DART stands for Double Asteroid Redirection Test. It was a test of planetary defense. The idea is you crash into an asteroid. It's a binary asteroid, so you crash into the smaller movement called Dimorphos. And it's hitting at about 15,000 miles per hour. We'll be able to tell how effective this was in altering the orbit by watching the period. The small asteroid comes around, it blocks light from the big one, so you can see a variation in the light. And that's the same way you detect planets.
It was expected
that it will change it from 1 to 10 minutes out of a 12-hour period that it currently has. This thing was launched back in 2021 in November.
It uses a camera to guide itself in and to do the crash. Essentially, that's missile technology. Usually most things you think of as being guided by GPS, but that's always been an alternative. As you match a picture, you essentially just aim for the center of a picture, and so they have the controls to do that. And I think they actually use some old missile control software for that. This had to be completely autonomous once you got within about 4 hours of impact. The transmission time, you couldn't possibly control it remotely, so everything was autonomous after about 4 hours before the impact. Now, how are we going to tell what happened? Well, there's a variety of ways. The Italians have built a small CubeSat, a very small satellite, about 10 units. For a CubeSat unit is 4 inches cubed. It's a light satellite that was dropped off about 15 days before the impact, so it'll watch it, and it did. It took pictures before and after, and it's hanging around in that area. There will be a follow-up mission out of the European Space Agency, specifically by Italy, a project called Hera, and they're going to go visit it in a few more years. At least they'll launch the craft to go visit it in a few more years. A few statistics I didn't mention last time. So we're hitting this moonlet called Dimorphos, and it's about 535 feet in diameter. They estimate it weighs about 11 billion pounds. Okay, so even that's a small asteroid. It's a lot smaller than what killed the dinosaurs, but still a lot of pounds. By comparison, we're hitting it with something that weighs 1,100 pounds. So it's a factor of 10 million difference. So you better hit it pretty fast if you expect to see much of a change. And that's why it is hitting it around 15,000 miles an hour, which isn't that different than the escape velocity from Earth in the first place. So I will comment, this was an artist's illustration. This is the one they've used for the last couple of years when talking about this project. And if you look kind of closely at them, Dimorphos in particular, it doesn't really look like this picture. Nobody really knew what it looked like until we just got there just now. If you've looked at other previous asteroids, this is basically Ryugu, which was an asteroid that the Japanese landed on and took a sample and came back from. So they had close-up pictures, and they pretty much stole that, figuring, okay, let's just pick an asteroid, and that was it. So there's what it really looks like, this egg-shaped thing on the left-hand side. And then as it was closing in, this picture was taken 2 seconds before impact on the right-hand side. This is what it looks like. It basically looks like a bunch of boulders. And in fact, they call it officially, the technical jargon for such a thing is a rubble pile. So, you can impress your friends with technical jargon. This is actually called a rubble pile. So why do we need DART in the first place? Well, first of all, asteroid hits have happened before. It will happen again. This proves that we can hit even a small and distant target, which, might have been questioned, say, 20 years ago. So now we've definitely proven we can do at least that much. But the real question will be, how effective will it be? And a lot of that depends on what the material of the asteroid is. For instance, if it's a really hard rock, and there are some of those, like the Psyche asteroid, which is thought to be mainly a former molten core of a planet, pretty metallic, that's really solid. If you hit that, there's an artist's conception of what would happen in the upper left corner of this slide. The idea was you'd hit it, and it would probably just shoot out a little bit of material, just kind of in one fairly narrow little beam. That actually would make the DART impact more powerful. Essentially, you get an extra kick because not only are you hitting the planet and transferring the momentum into the planet, but the fact that some of it shot back the other way by balance, in effect, it applies more force. So that would be good if it's a really solid asteroid. Unfortunately, it's looking like the typical asteroid is probably a rubble pile, meaning they're really a bunch of boulders that are held together by gravity, somewhat loosely. And this one might be it. The worst case, a craft might just go right through it. For instance, it would be hard to land on it. That's what they found out in the last couple of asteroid sampling missions, both Bennu and Ryugu. They tried to land, and they had a hard time even landing or drilling into it because it's just such soft material. What are alternatives for changing the course of an asteroid? Well, one that you always see in science fiction movies, besides hitting it and blowing it up, the other thing is put a rocket engine on it and turn it on and just have it go away. Well, if you just got a pile of rubble, that's probably not going to work. You'd probably just kind of push your way through the rocks, and that wouldn't work at all. If you blow them up, they could actually just recoalesce, and that supposedly happens upon impact. Yeah, they'll go apart, but eventually they'll just work their way back. And it might only take hours, it might only take weeks. But in any case, you wouldn't have accomplished a whole lot. We needed to get some real-world experience with this, get a feeling of what's going to happen. Now, they have actual pictures taken from the Lichia cube, the Italian CubeSat, and that's on the right-hand side here. The big one in the front, of course, that's the main asteroid, but the one they blew up is the one up here on top. And it looks like there's stuff just shooting out almost every direction. They call it a crescent because it's one little area that maybe it doesn't. But that would probably indicate this thing was a pile of rubble, pretty loose. So it's kind of hard to say what'll happen. And it's especially hard to say what'll happen because it's a binary asteroid. You can move stuff around, but some of that's going to hit the other asteroid and change it. In any case, even just through normal gravity, you try to change the path of one, you're going to pull the other one along. You put a big rocket on the moon, you would drag the Earth to some extent with you too. So there's going to be a lot of interactions. It'll be very hard to really model this very effectively. People have tried, of course, but you just don't know what will happen until you try it. So there's a couple of obvious issues with this kind of planetary defense. The first one is, well, obviously you've got to detect the asteroids way ahead of time because you're not going to be able to change their orbit or their path very much. But the theory is if you do it early enough, you don't have to change it very much. So that means you need to detect them early. Then the second thing is characterizing them. If you don't know if it's a pile of rubble or a really solid thing, you're not quite sure what's going to happen. So all those things will still make planetary defense hard.
Doug Hall had a question about how much advance warning we really need for asteroids.
Years, decades, ideally. It depends. If it's something that came in even from outside our solar system, yeah, who knows? I mean, it might only have a little bit of time. But, most of them are assumed to be in orbit, but just not noticed yet. Well, yeah, how do you estimate how many are unknown? I've seen wildly varying estimates. Yeah, they think there's probably a lot of them out there that they just don't know about. There's a project called the NEO survey, or a near Earth object. The reason you can't see a lot of asteroids is they essentially go inside the orbit of the Earth. The problem is you look that direction, you're looking toward the sun, and so they pretty much get blocked out. So the idea was, well, why don't we put something in between the Earth and the sun at the L1 point? That's a great idea because as the Earth rotates around the sun, it stays in constant distance so you can exchange data very easily. And it can look back. And so this craft would be designed very much like the Webb Space Telescope. Big solar shades on the side facing the sun, and then it would be facing outward, typically looking before and after the Earth orbit, and have a good view of it. So that was the idea. They set up a program to do this. First of all, there was a mandate from Congress back in 2005 saying that we should find 90% of these things. Obviously, again, how do you count? Who knows? But the idea was look a lot harder. But the thing is, they said that, but nobody ever really funded it, and NASA didn't really push it either. Like, nobody was really that interested in doing it. Well, then in 2019, we had one of these near misses where there was an asteroid that came actually in between the moon and Earth, and it was a surprise to everybody. Nobody even knew it until almost right before it happened. So that kind of woke people up a little bit that, yeah, maybe we better think about this a little more carefully. So what they want to do is they want to catalog all the near-Earth objects, meaning by their definition, larger than 460 feet. That it's some translation from meters. It's a round number. And within about 30 million miles of Earth's orbit. So things that might possibly threaten Earth. And we'll see what happens. Congress really didn't push it. NASA didn't push it. But now we really think we need to. They're getting some funding, so they're doing design work, but they haven't really fully funded this program. It is an official position of the National Space Society. They are lobbying, along with other organizations like the Planetary Society. Yeah, in this picture here, this is just a visualization of the asteroid belt, which would be the main asteroids. You got the sun in the center there. Most of these asteroids are the ones between Mars and Jupiter. Now, of course, there are other things that could come in. They could come in from out in the Kuiper belt or whatever it is. Lots of other places, but at least a lot of them haven't really been cataloged yet. They will come, and yeah, maybe every 65 million years you get one that dinosaur killing size. Nobody knows.
Doug asked for details about the 2019 near-miss asteroid. It passed within the moon's orbit, within about 44,000 miles. That's only 1/5 of the distance from the Earth to the moon. The estimated diameter of that asteroid was 200 to 400 feet. If it were 330 feet in diameter, 100 meters, it would have released the power of a 50 megaton bomb. The scary thing was that it only was discovered the day before the near miss. Doug pointed out that only looking for near-Earth objects bigger than 460 feet isn't really good enough. The 60-foot diameter asteroid that hit Russia in 2013 caused an explosion 30 to 40 times stronger than the Hiroshima atomic bomb and injured 1,200 people.
Well, what they said was that they had to catalog the ones that are bigger, but what they're saying in the actual program, they think they can get down to about 100 feet. So at least it's getting closer to that. Now, one thing about this, it uses an infrared telescope. You can't do that too well on Earth because the atmosphere gets in the way too well. You want infrared because most asteroids are black, or at least very, very dark colored, and it's hard to see them. So, but in infrared, they're still emitting plenty of heat. And so that's why it's important that it be an infrared telescope. And I think it uses a couple of infrared bands to actually accomplish this. So interesting project. Is also just interesting that it never really got serious attention, despite even a congressional mandate back in 2005. So back to the planetary defense thing. We crashed into an asteroid, everybody knows that, but what was the final result? I put in the actual images, incidentally, instead of the original artist's conception, because that's what they really look like. The small one is more detailed because we crashed into that one, so we have a more close-up picture. The effects have been recorded by a lot of different organizations. The Hubble telescope, the James Webb Space Telescope, all looked at it. And there are several dimensions to this. The first part is, what was the orbit of the smaller asteroid after the crash around the larger one? And that is measured just by looking for, if you can see a dim spot in the sky, which represents that pair, you can't actually distinguish between the two. But you see the light, and when it gets dim, that tells you that, okay, the smaller asteroid passed in front of the bigger one. And you count, you see how long that takes. And so that's one way they looked at it. And we'll talk about some other things they're doing. It turned out the effectiveness of this experiment was more than we had expected. The orbit of the smaller asteroid is about 12 hours around the large one, a little bit less than that. And it reduced it by 32 minutes, which is kind of noticeable. Why? Probably because the asteroid itself is in a category called pile of rubble. It's mostly a bunch of boulders just kind of held together by gravity. You smash into them, you knock a lot of them out of the way. So you imagine if you have an asteroid coming this way and you're trying to slow it down, you hit it, a whole bunch of rocks get thrown out into space. Based on conservation of momentum, that actually kind of gives you a little extra kick. And that's pretty much what they figured happened. That turned out a lot better than they expected. As long as all those particles don't spread out symmetrically, you definitely get an effect in one direction or another. Now, the second question, though, is, okay, that's all well and good, but what about the overall combination of the two asteroids? People might think, oh, well, you're hitting the little one, there's no connection with the big one, but there is. They're held together by gravity. It's just like being held by a string, really. They affect each other. So the question is, for that overall pair, did it affect the orbit? And that's going to take a lot longer to tell. I mean, the orbits are pretty slow. So that'll go on for actually over the next couple of years. How did they even tell that? Well, as another one of these kind of things we talked about, instead of dimming of the light coming directly from it, what we watch instead is we watch for the path of the asteroid to cross in between us and some other star. And all those star positions are well known. And so when it gets dimmed, right about the time when you might expect that the asteroid is going by, you can pinpoint the time, and you do that a couple of times, and you get a pretty good idea of how the orbit is going. So the European Space Agency, ESA, they've put together a crowdfunding kind of approach where they just want lots of even amateur astronomers to contribute to this. And so they're doing that, and they hope to come up with better answers on how much the overall orbit was affected. So one interesting thing is, what does it look like right now after the crash? That's this picture here of the blue kind of thing. And if you look at it really closely, there's actually two kind of comet tails coming up. They're both about 3 o'clock here, just above that. But there's actually two of them. They haven't actually really figured out why. The second one appeared later than the first one. So it's a little bit of a mystery, but that's what science is all about. You go out and you blow up stuff and you see what happens and you try to explain it. That's science in a nutshell. So they will explain that, but they haven't yet. And incidentally, then there's just a little picture over here in the lower right of imagining what it looks like when an asteroid crosses in front of a star. It's kind of hard to see the little star there, but it's working in the background.